Hello and welcome. In this video I want to talk about the curl of a vector field. I'll jump right in with a definition here. Uh, curl is generally a 3D concept here, but we will modify it slightly to make it a 2D concept as well. But if you get a vector field in 3D, so P, Q, and R are the components of the vector field, and each of those have appropriate partial derivatives existing. So P has to have partial with respect to y and z existing. Q has to have x and z existing. R has to have x and y, those partial derivatives existing. Our textbook actually doesn't list all 6 of these. It only lists 3, but you need all 6. If those all exist, then we define the curl as follows. The curl of f, which I also will denote as del cross f, as you may recall from divergence, del dot f was the divergence. Del cross f is now going to be the curl. And it is this. It's a vector field again. So the divergence of a vector field was a scalar function, but the curl is going to be a vector field. And the first component of the vector field is partial of r with respect to y minus the partial of q with respect to z. Second component is the partial of p with respect to z minus the partial of r with respect to x. And the third component is the partial of q with respect to x minus the partial of p with respect to y. How would you ever remember all of that stuff? Well, there's an easy way. Because if we think of this del operator, this grad, we used it for the gradient, we've now used it for the divergence, and I'm about to use it for curl here, right? If you think of it the same way as this vector, partial with respect to x, partial with respect to y, partial with respect to z, again, put big old quotes around that word vector, because this isn't really a vector, it's an operator waiting for something to be put into it, right? And if you just think about how you would cross two vectors, right? You put ijk up in the first, you make a determinant here, ijk, and you put the components of the first vector, so partial x, partial y, partial z, that's the second row of this matrix, and then the third row is the PQR from that second vector. Okay. Now, this looks like a determinant, but this is kind of ludicrous. I mean, determinants are a way of taking a square matrix and turning it into a number, right? There's a method of doing this. This is not a square matrix of numbers. This has got vectors in the first row, it's got operators in the second row, and it's got, well, these are at least real valued functions, p, q, and r, so those at least are kind of like numbers. And my battery just died on my light. Oh well, I'll be in the dark here for a while. But how do you do a determinant, right? I'm going to expand across that first row. So I've got the vector I times whatever this little 2 by 2 subdeterminant is here. Well, that just means that that little 2 to 2 subdeterminant is going to be in the first component of my vector, right? And then you're going to have minus j times another subdeterminant, and then plus k times a third determinant. So those are the 3 components of your vector. The first one with I, the second one with j, the third one with k. So the first component is here, this. So these 2 multiplied together minus those 2 multiplied together. Again, multiplied's got big old quotes around it because you're not multiplying. You're taking the partial derivative of r with respect to y and then subtracting the partial derivative of q with respect to z, right? So that's that first one. Now, it's minus j times this other determinant, so I'm going to do this determinant backwards just to get the minus sign in there. So it's the partial of p with respect to z minus the partial of r with respect to x. There's that one. And lastly, so partial of q with respect to x minus the partial of p with respect to y. Okay. This is the way I think of it every time. I have trouble just remembering that formula, but I don't have any trouble doing this. I know how to do determinants, and I am writing the notation in a way that helps me figure out what I need to do, right? This is acting like a cross product, so I'm going to write it like a cross product. All right. If what we have is just a two-dimensional vector space, sorry, two-dimensional vector field. So f is just a function of x and y, and the output is just, p and q, so you're only in the xy plane. I essentially think of this as embedded in 3 dimensions. So it's p, q, comma, as p, comma, q, comma, 0, right? So the z component is 0. And p and q are still functions of just x and y. So when I do this, this partial of r with respect to y, well, r is 0, so that's a 0. Partial of q with respect to z, well, q is not a function of z here, so that partial is 0. Likewise here, partial of p with respect to z, that's 0, because there's no z's in the p here. And partial of r with respect to x, well, r is 0. It's just the function 0, so that's 0. And so so you get 0, 0 for those first 2 components, and then you get this partial of q with respect to x minus partial of p with respect to y here in that 3rd component. So in the event that you're dealing with just a 2-dimensional vector field, the curl will be a vector that's completely perpendicular to the xy plane. It's either pointing up the z-axis or down the z-axis, depending on whether this stuff here, partial of q with respect to x minus partial of q with respect to y, whether that's positive or negative. Okay. And what the heck is this telling us? Well, let's take a look and see here. Let's do some examples. First example I want to look at is just in the plane. It's easiest to see what the curl is doing when you just look in the plane. When you start trying to draw these vector fields in 3D, oh my goodness, it gets complicated fast. So we're sticking just in the plane here for now. Y comma 0. So it's this vector field here. I'm going to zoom in on it a little bit here. So these are all running sideways. When I do sorry, I didn't look at the calculation. When I do the gradient, not the gradient, what is this? The curl. So I'm following these things here. Partial, no, actually I'm just doing this one right here. It's 0, 0. And so I need the partial of q with respect to x. Well, that's 0. And then the partial of p with respect to y, that's 1. So 0 minus 1 is minus 1. So 0, 0 minus 1 is the curl. So everywhere it seems that the curl is pointing in the negative z direction, just length 1. Now, the way I think of this with the right-hand rule here, since x is off to that way and y is off to that way, then z is pointing into the board, right? And I'm pointing at myself because I'm actually in the screen, right? I'm looking out at you. So the screen is out here and I'm back here. So I'm completely behind it. So I'm pointing at me, that's away from you. Or if I'm pointing at you, that's away from me. So pointing towards you is out of the screen, pointing towards me is into the screen. Okay. If you think that's confusing, try looking at it from this side. Yeah. So -1. So it's pointing into the screen. So let's go back over here now. I have the option here of showing the curl at any point. So if I click on a spot here, editor Will here jumping in. 1, my light is now fixed. But 2, you're about to see a bunch of little spinning paddle wheels. And live, they look awesome from the point of view of watching a video, which is a strobe because you're watching individual frames. They don't always look like they're supposed to look. They don't always look, even when they're spinning one way, they might be looking like they're spinning the other way. Just like any time you see something spinning on a movie or a TV show or something like that, you're watching it through a strobe. So they don't look right. However, if you are actually taking my class, right, and you have access to the webpage, in the content section of this, whatever week this is, you can click on Will's Notes and go down to the section that this is from and click on that, and then the links are actually active. When you click on a graph, it takes you to calc-plot 3D and you can see the graph, and you can say, show me the curl, and then click on points and watch the thing spin yourself. It's going to be so much better than watching these spinning wheels through strobes. Okay. Anyway, I realized that after this video was made. So here we go, back to the video. It puts the little paddle wheel there. And what the curl is indicating is a tendency to spin. If you think of this as flowing water, and these vectors are velocity vectors, right? So here, essentially the water is not moving at all along the x-axis. As you get further away from the x-axis, it's moving faster and faster and faster, always just horizontally, right? Likewise down here, it's flowing in the other direction, but still horizontally. And in some ways you might think there's no tendency to spin there because everything's moving in the same direction. But the higher up stuff is spinning faster than the lower, sorry, is moving faster than the lower down stuff. So an object that was floating down that stream would have a tendency, I guess I should be going the other way because I'm behind here, would have a tendency to turn because the top part is trying to go faster than the bottom part. And so there's some spin. And the right-hand rule is saying you need to take your right hand and make it curl, make your fingers curl in the direction of that. Well, there's two ways to think of it. I know that I calculated that the curl was negative z. So if I point my thumb, my right thumb, in the direction of negative z, which I'm pointing towards me because that's into the screen. For you, it's away from you, into the screen. Look at the curl. My fingers are curling in the same direction that paddle wheel is spinning, right? Just pointing at the screen doesn't do you any good. That paddle wheel over there is spinning, right? It's going this way. This is so hard for me because when I look at it, it's going backwards, but my image is doing it right. It's going, you're seeing it as going clockwise, right? It's spinning clockwise down. My right hand, my fingers are going in the direction of the spin. My thumb is pointed right out at me. That's the direction of the curl. So the curl is the curl vector is the axis that the spinning is happening around. Okay, and when you're just dealing with a vector field in the plane, you're either going to be spinning around something in the negative x direction, or you're going to be spinning around something in the negative z direction or the positive z direction. That's the only options here. Okay, and this one, as I move around, as I move this around, it always spins at the same rate. Right? It's always got that curl of -1. The magnitude of the spin isn't changing. Okay, so let's look at another example where maybe that does change. So rather than this, let's change that to a y squared. So I still have just horizontal motion, right? Everything's just flowing off to the, what direction is that? To the right. Okay, moving faster up at the top and 0 down here in the middle, but the bottom is also moving off to the right now because the y squared is always positive. Finding the curl, again, partial of q with respect to x minus the partial of p with respect to y. This time the partial of p with respect to y is 2y. So this is negative 2y. So again, this should have a, and the direction of the curl is going to depend on y, into the screen if y is positive, out of the screen if y is negative. Okay, so let's click on this one and see. Yeah. Okay, I don't want flow lines, I want the curl. So when I plop this curl thing in there, yeah, sure enough, it's spinning clockwise. If I move this around, plop it up here, it's spinning a whole lot faster, right? Because remember, the curl was negative 2y, and so for bigger values of y, you're getting a longer curl vector, which means it's spinning faster. There's a higher tendency to spin up here than there was down close to here. In fact, if you stick this on the origin, or on the x-axis, it shouldn't be moving at all. But when I come down here now, plop it down here, it's now spinning counterclockwise. So if I can get my fingers to move in that direction of that motion, my thumb is now pointing out at you, right? If I can do this, wow, there, it's coming straight out at you. This is um, rotation in the other direction. So this counterclockwise rotation means that the normal vector is pointing straight out at you. Right? Rotation up here is in the other direction, and the curl points into the screen. Again, we get really fast spin, way out on the edges here. Right? Very slow spin in there. It's just a matter of what's the differential in how fast it's moving on one side versus the other side. Now, in some vector fields, it actually is completely spinning around. So let me give you an example of one that clearly looks like it spins. If I just do this y comma negative x, which we've seen many times, right? This certainly is spinning. If I put my point right at the origin, right, that's clearly spinning around. Out here, spinning, trying to see, it seems to not change at all. Well, let's see. Partial of, we're using n, p, and mn and p, but anyway, this would be the partial of q with respect to x is -1, and the partial of p with respect to y is 1, so -1 is -2. This is constant curl, -2, so it's into the screen with amplitude, with a size of that vector of 2. Constant curl everywhere. Let's look at one example in R3. I'll get my face up out of the way here. So this is my one example in R3. I'm doing f of x, y, z here is yz, comma, minus xz, comma, minus xy. To take the curl of this thing, I'm going to set it up like a determinant. And here we go. The first component should be the partial of minus xy with respect to y, which is that minus x right there. And then I'm going to subtract the partial of minus xz with respect to z. So I'm subtracting another negative x, which ends up adding the x. So that's going to turn into a 0. And the middle one I always do backwards because it's minus j times this determinant. So just do the determinant backwards to take care of the minus sign. So this is the partial of yz with respect to z. That's just this y right here. And then I'm going to subtract the partial of minus xy with respect to x, which is minus y. So I'm subtracting minus y. So that's a plus y. And so that turns into a 2y. And then lastly, I've got the partial of minus xz with respect to x. That's minus z right there. And the partial of yz with respect to z is z, and I'm subtracting, so minus z is minus 2z. So that is that is the curl field, right? So the curl in 3D is a vector, it's a vector field. So at each point, there's a vector pointing out some direction. And what we're saying is that the rotation, that's the axis of rotation. That at that point where that vector is being calculated, you're rotating in a plane that's perpendicular to the curl vector. And the magnitude, sort of the speed of the curl, the speed of that rotation is related to the length of the curl vector. This is just, it's really hard to see in 3D as to what's going on here. So there's looking straight down the x-axis. It doesn't really look like there's that much spin in that direction. Ooh, but down the y-axis there's definitely rotation. Looks like there's rotation one way in the front, one the other way in the back. If I look down the z-axis, oh, there's some rotation there as well. In fact, it's really pretty cool if you look down here. Oh, it's gonna get this. Yeah, let's look at it like this. So where is things? The z-axis pointed that way. The x-axis is pointed up. Oh no, maybe the z is pointed back and the y is right here. Anyway, I see I see a couple of whirls going like this and that. Same thing here. Now it's going up. So it's like it's going up on this at this edge, but it's coming down on that edge. And I think it's going up in the back and down there. So there's just this different swirling all that's going on. And if I show the curl vector, it gets really really hard to see. But notice that curl vector, they're all flat in this direction. The x component is running up and down at the moment. So the x component was 0, and the y and z components are, there was 2y and 2z, or minus 2y and minus 2z. Actually, it was 2y and minus 2z. It's just hard to see. Someday, I'm going to have VR goggles to hand to all of my students, and you're going to be able to get in the 3D space and see these vectors and see here's the curl vector going this way, and the rotation is around that curl vector, right? Or the curl vector is going over that way, and the rotation is around that. But when you try to draw it on the plane, it's just hard to see. You got to take my word for it, which I hate to say, but I try to be good to my word. Yeah. How the heck is this rotating? Yeah, it's just so hard to see. But that's what it is. You're creating a new vector field, and that vector field is giving you an axis that the original vector field is rotating around at each particular point. Okay. That is the curl.